here we can implement Knn Ii model in scikit-learn using the Euclidean distance matrix. We from the scikit-learn neighbors import Knn Ii classifier, and here we generate an object Knn, okay, from the class Knn neighbor classifiers. And here we must set several parameters. Here, n neighbors is the number k in the previous slide, and the p equal to 2, and the matrix is Minkowski. That is, we select the Euclidean algorithm. Okay, the Minkowski distance we will discuss later. And here we use the function fit to train the data. And how to train data, we use the X train standardized and Y train. So X train and Y train is we divide the data in original data into two parts. One part training data and another is testing data. And for the training data, we must transform the training data to standard normal distribution. So the transform data we give a name STD. Okay, and then the following program is just plot the decision region. Okay, for us to consider to understand the decision region for the Knn neighbor algorithm. Okay, so if we use the matplotlib to plot the decision region for the iris data set, we can see here have 3 regions. Okay, and this region, the boundary of the region, not like the precision or logic. This not the line. Okay, maybe here because this point decide the region based on the nearest neighbor. So the region between the boundary class 1 and class 2 not a line. Okay, it's a complicated shape here. Okay, so maybe sometimes the data you can consider here for the Knn neighbor classifier, you will the boundary not a line, and sometimes the boundary will be a very complex shape because the shape here, the boundary, not any linear function. So this shape very depend on the training data. And the Knn neighbor algorithm sometimes very sensitive to the training data. And the Knn neighbor maybe make the overfitting. Okay, we will talk about the overfitting. Have a very dramatic generate result overfitting. Okay, some important concept we need to discuss later. How to avoid the overfitting. Okay, essentially use the Knn neighbor algorithm. Okay, now we will discuss the number k and the distance matrix in Knn neighbor. The right choice of k is crucial to find a good balance between overfitting and underfitting. We have to make sure that we choose a distance matrix that is appropriate for the features in the dataset. So at previous slide, we have talked about Minkowski distance. So what is Minkowski distance is the distance defined by this formula. So we can see if we take the number p to be 2, here is the difference of coordinate square sum take square root. Okay, so based on the definition, this is the standard Euclidean distance. Okay, so what is the Euclidean distance? If we want to measure the distance between 2 points, we just use a line connect to the point and measure the length of the line. So the length of line between this point is square, summation of square, different square take a square root. And the other distance is Manhattan distance. So Manhattan distance is here. We can see if we want to measure the shortest path from this point to this point, and the path based on the contraction here, restriction here, the path we can go only to right or to up. Okay, we have another way to go from the point to the point. So here we just can go right, up, right, up, or right, up, right, up. Okay, so we have a step up option to go from this point to this point, but all the options we just can go to right or go to up. Okay, so what is the mean maturity pace? Based on we can go to up and go to right and go to up from this point to this point. Or this is the Manhattan distance. So what is the minimal distance? It is the difference between the x coordinate plus the difference between the y coordinate. So here we can know, we just calculate, we just let p equal to 1. So here you don't need to take the root. We just here the number p is 1. So we just take the summation about the sum about the difference of each coordinate. So this is the definition about the Manhattan distance. Here we can find the distance matrix available in scikit-learn in the following URL. So we know, we have see from the diagram decision region for the k-nearest neighbor. We can see the k-nearest neighbor will form the very complex boundary for the region. So the k-nearest neighbor will generate overfitting, or if the data is high dimension. So this is curse of dimensionality. What is the curse of dimensionality? That is, the increase in the data dimension results in exponential increase in computational expense. And the increase in the data dimension leads to overfitting. So the machine learning model will increase in complexity. Okay, so will lead to overfitting. And we need, for the increase of the data dimension, we'll need an exponential growth in number of samples. Okay, so the k-nearest neighbor classifier is very susceptible to overfitting due to the curse of dimensionality. So how to avoid the overfitting? We have several methods. The first one, regularization. This regularization can be adopted by logic regression, but this method is not applicable for k-nearest neighbor decision tree. Because this kind of model is a parametric model, and this kind of model is non-parametric model. The regression method can apply for parametric model, but for k-nearest neighbor decision tree, this kind of model is non-parametric model cannot be used regression. Another method to avoid overfitting is feature selection, dimensional reduction technique. We use the feature selection dimensional reduction technique to avoid the overfitting.